they arrive. So, tēnā koutou katoa, nau mai haere mai. Welcome everybody to this webinar, which is one of our designer webinars in the series of 2025 webinars put on by the Passive House Institute New Zealand. We're very grateful for this webinar to be sponsored by Stark Windows. And the subject of this webinar is Windows are vital but complex. And just a little bit of housekeeping information. So attending this webinar, you can get 2 PHI CPD hours. So if you're a certified Passive designer or consultant or tradesperson, you can get those credits. If you're a registered architect, you can get 15 NZRAB points. If you're registered with some other profession, you're quite possibly able to get your CPD credits as elective hours. The recording, this webinar is being recorded. The recording will be available from Monday for those that have registered for it. It'll be made public some point later down the track, but it's kept exclusive to those that have registered to attend it live as a recording in the first instance. And we really encourage lots of engagement in these webinars and discussions. So the presentation itself will run for around 60 minutes, and then there'll be around 30 minutes for questions and answers and discussion. If you use the chat function, which is down the bottom of the Zoom window, then you can add your questions within there. I'll keep a track of what's going on there, and then we'll pin down the presenters at the end and make them answer your tricky and difficult questions. Can we have the next slide, please? Okay, while that's being organised. Right, here we are. So, speakers, people today, who am I? I'm Elron Burrell, I'm a board member of Passive House Institute, and I'm hosting today, so I'm just talking very briefly, then I'll shut up. We're very grateful to have Jason Quinn from Sustainable Engineering, who is a Passive House designer and Passive House certifier and building scientist, generally very well known in New Zealand. He'll be the main presenter today. And we'll also have Benji Simmons, who is from Stark Windows, sponsors of this webinar, to give us a brief talk about their windows as well. And just before we hand over to Benji, I just want to say a couple of things about today's webinar to sort of set the scene a bit. You may have heard a very famous quote that our eyes are the windows to our soul, sometimes attributed to Leonardo da Vinci, sometimes taken back before him. And if that's the case, then perhaps windows are the insights into the performance of our buildings, because no matter how good our windows are, there's still holes in the thermal envelope. And if you look at the performance of a very high performance window and compare it to the performance of a wall that it's within, usually it's still not anywhere near the performance of that window. So they're incredibly critical parts of the performance of a building, letting light in, giving us views, all sorts of other functions. And aside from that, they're also quite complex beasts in themselves. They're not quite as simple an assembly as, say, a roof or a wall. Lots of different parts to them, some moving parts, different materials, etc. So there's lots to get through in this webinar. And as I said, we're very grateful for Stark to be sponsoring the webinar today, helping bring this about. And I'll hand over to Benji now to just say a few words.
Amazing. Thank you, Elron. I just can't see the slide, so I'm assuming it's showing the next one.
We've got your slide on screen, which shows the ambience and the commercial. Thank
you so very much. I couldn't have introduced it any better myself, but I was going to say a quote that has been bandied around before, is in line with what you're saying, is that windows are the most expensive part of the envelope and they're also the worst. And you know, we're aware of that. And in some ways, it's a burden of responsibility that we do the very best we can there. And it's not only heat loss, but it's also obviously heat gain in terms of the solar heat gain so often. And another quote that I was thinking I might bring in terms of change, because just a little bit for those of you who don't know my company Stark, we were a very traditional aluminium window fabricator since the 80s, and it was about probably 5 or so years ago we began to have an awakening about the thermal performance, particularly of our windows, and we looked around the world at what better or best practice was, and we looked at our own market and you know, just how bad things were. And I paid particular attention to the Passive House community, and this is probably about 2019, 2020. And so often windows were such an incredibly difficult part of building a passive house in New Zealand at that time. And a big part of what we set out to do in bringing better performing windows to New Zealand was to try and solve that problem for the passive house community as well. So that was not only the windows and the fabrication and the price and all these things, but it was about getting that data, which Jason can probably speak to. And there's a lot of data and it's pretty complex and it's easy to get it wrong. We've done our best to get all the data we can, and we continue to get more and kind of verify it. But the quote I was thinking of back then when I was kind of studying the market and trying to work out, it was actually Bob Burnett, I believe, said that in order for change to occur, we need education and legislation. And I added to that we need some commercialization, which is kind of where we come in, because if it's not available at the right price point, it's not going to get built. So I think that's obviously today is about education, and there has been legislative change in the H1, so that's kind of improving things. But we as a company are about making the product and making it well and making it available at the right price point. So really looking forward to listening to Jason and all the technical, and I'm happy to chip in with any other questions as we go. But as you can see there, just one final thing, we're probably most well known for our UPVC offering, but we also have a range of very high performing aluminium systems that we can explore. Now those come at a significantly higher price point, but they do have some performance metrics that are not available in the Ambience UPVC. So happy to discuss that as well. And over to you, Jason, for some educational content.
Well, thanks, Mindy. Thanks for that. I will go ahead and share my screen. Yeah, it's good to show folks cross sections of the UPVC, and then are you okay with the brand name? You can nod or not nod with the aluminium series.
Yeah, sure.
Yeah, so that and those high performance Rainers aluminium profiles. So folks might not know, but I've got a couple cross section of windows in my basement I have since 2010 or so, and I've brought them out at various times. And one of which is basically equivalent to the UPVC profile that you offer, as well as a high performance Rainers assembly. And I've had that for a very long time. It was gifted to me by a window supplier in the US. Anyways, let me see if I can get this screen to share. Let me go, screen 2, that should work. All right, and so I wanted to take a few minutes to go through this and kind of lay the foundation, as it were. This presentation is a teaching seminar for me, right? So it's an opportunity for me to help educate folks on Windows, the things that are quite complex about them, and some very common pitfalls. And I really do like that quote, Benji, about commercialization as a function of education and legislation, is how I'd flip that around. But you can look at it from both perspectives. So I wanted to ask first to pull a poll together. So I've asked PHINZ to go ahead and run a poll on Zoom. So if you could take a few minutes and answer that, we'll go ahead and carry on through the slides, but I just kind of wanted to see who the folks are on the webinar. And Aaron, if you could, when that poll's finished, I won't get to see the results because I've got the screen sharing stuff with Zoom. If you could go ahead and just interrupt me and tell me where we're at with folks. And not in a hurry, but at some point in the next few slides, if you can, whatever you think is appropriate. So this presentation is effectively a simplified excerpt from our Passive House in Practice course, which is intended to follow on from the Certified Passive House Designer training. And it's basically a mentored approach where we take folks through their first Passive House project all the way through certification, submission, that is. So we've got it, and it's what we do with our own staff when we've got a new person join the team who wants to become a Passive House designer. We kind of have a process they run through. Because although the building science taught in the Certified Passive House Designer course is amazing, and it's really well, and there's not much I can think to change on that. The processes and tools you use in actually getting your first project can be quite stressful and dramatic. I know my first project in 2012 was pretty stressful for me. So that's intended to do that. And this presentation is effectively a cut down version of the Windows session of that course. All right. And the first point I'd like to make is that windows are the biggest impact on buildings. I mean, you heard Elron spoke a few minutes about them being the worst holes in the wall. They also can get a lot of energy in. So this is an energy balance for a certified pass house that was designed by Toby Brook, who's overseas somewhere living his best life at this moment. And you can see the windows in here. The gains are on the right-hand side. Those are things that keep the building warm over the heating season. And the left-hand side is the losses. And you can see for these certified passive house windows, they actually make the building better, right? And that's and they, in other words, they gain more than they lose. Now, if you've noticed in the same graph, this top little bar up here is white, which basically I try to simplify to clients and say that's the heat you throw away in the winter, all right? So when the bar starts, this bar starts getting big, you're getting this free heat from this windows in the yellow bars, that 45.3, but you can't overdo it because you tend to cook the building. So windows are an impact, and you need to adjust by getting the performance level right. And that's often what we do across the country. All right, so let's talk about pitfalls. And I don't know if you guys have had any fun with some of the image generators, but I used to play Pitfall when I was a kid, which tells you how old I was, because that was in the original Atari 2600, where it had like one button you could mash, and you jumped over a little. Anyways, I won't go into Pitfall too much. Anyway, so that's what we think when people talk about pitfalls. So the primary pitfalls, I'll bring the slide up over and over again, and we'll kind of go through the pitfall that comes with it. When we're doing certifications, when we're doing designs for our own projects, one of the first problems we run into is measuring things. So if you get an architectural set, are the window sizes on there the actual frame size, the net frame size, or the rough opening size, or some other crazy size? And you would think this would be pretty straightforward, but it is not. In other words, it gets screwed up all the time. There's a reason you have to sign your window quote and send it back to the window manufacturer before they make it, because they're like, if you want a different size, it's your fault, not ours after that. And that's because this size gets screwed up so much. So the size that goes into PHPP is the net frame size, which is if you had the windows on the sawhorses next to the building, you could measure that. You don't measure the building, you measure the window frame, right? The other way to think about it, I'd like to say, if you could magically laser cut a hole in the building, that's the smallest hole you can just kind of squeak the windows into, right? And that's the window size that goes into PHPP. There's other sizes, of course, and we'll talk about how those affect performance and get into all those details. But literally the first pitfall you run into as a passive house designer is what hell size the windows are, which is pretty entertaining, but we just need to be clear. And it doesn't help that the Germans keep using rough opening in the passive house planning package manual, which confuses everyone, but it's net frame size. It's very clear. Okay, first pitfall accomplished. The next one is, I don't know how much folks have played around with passive house planning package 10. Some of the passive house designers have been around since 9, or I started with version 7 even. Passive house planning package has this new multi-pane update in passive house planning package 10. And effectively it allows you to enter windows with this window here showing in height and width on the top right as one window. And that makes the thermal comfort calculation more accurate because it knows the whole size of the window. And that allowed them to basically allow us, it took away some of the exemptions for really small windows, but it also makes it much more accurate for thermal comfort calculations. However, if you're using design pH, which is a process we teach internally, and I recommend folks use externally, it can't handle multi-pane windows in design pH. So you have to make the choice to either, and this is the pitfall, in design pH, model the whole big window as one big window and get the shading factor, and then manually in PHP add in the other panes. Basically you're adding in these mullions and transoms. Transoms are horizontal like a letter T. Transoms and mullions, right? In PHP, which makes the results more accurate. You get better, it just works better if you can do that. Or, which we often do in our designs, is use passive house planning package 9 style, where each bit of glass is modeled as a separate window. So this would be 5 windows, not 1, right? If you're using passive house planning package 10 style, you need PHP 10 style data, which means you need data on the mullions and transoms, so you need to simulate it conservatively in your design. Not all window suppliers have that. Stark windows do, of course, and they're available in the database, so you can just drop them in, and I'll show you that in a few minutes. Another thing, another pitfall that gets people out and is actually reasonably important for overheating analysis is window frames suck, right? They're the lowest, they tend to be the lowest U value, the worst U value, the highest U value, the lowest R value in the whole building is the window frames. Occasionally you'll have double pane glass in a really good performing frame, and that won't be the case, but almost always the frames are the worst part of the building. So one of the improvements that's been done in passive house planning package 10 is basically the window frame color. So if it's white, I put in 0.25 personally, but it's somewhere between 0.25 and 0.4. And if it's black, like the series you can get from our sponsor today, then it's in the 0.8 to 0.9 range, right? And what you'll find is that if you have a poor performing frame, especially like a solid aluminum frame, if you're looking at an existing building and you put in a black frame, you'll get much more overheating because the energy is coming right in. And like everything in PHINZ planning package, this is not the reality. In other words, if you're sitting right next to that window, the impact can be much different because this is averaged over the whole building because the PHINZ planning package models for the whole building. All right, so those are kind of before you even get to the window supply and window data, these are kind of the big impacts that happen in your PHINZ planning package. Oh, Aaron, did you want to say something?
I've got the poll results if you want to know.
Yeah, if I could hear them.
So on the webinar today, we have builders at 5%, designers at 76%, window importers at 5%, window manufacturers at 2%, and people that don't fit into those categories make up 12%.
I really wonder who the other is. Is that just some people who didn't click the thing, or is that actually you think people clicked other? I'll have to think about that next time. Anyways, but that's sort of what I expected. Most of the designers, a lot of this stuff is quite practical. I know we've started out by talking about PHINZ planning package, but later on we'll get into more of the practicalities of Windows. One item that I'll mention here, but perhaps I should have mentioned it really early on when Benjay's slides were up earlier, is that we won't talk about flashing systems today. Right? That's primarily external moisture. I don't consider myself an expert in external moisture, but it is one big pitfall that occurs with Windows, especially imported Windows, is flashing systems. So it's important that if you are, especially if you're importing Windows, but even from a New Zealand supplier, even from a New Zealand manufacturer, that along with that window quote, before you take that price as being the price, that you look at the price plus any special flashing systems required. It's gotten a lot better in the last couple of years, but certainly we've had some windows that went into buildings that had European style windows installed halfway European and halfway Kiwi, and they did not work well. There was definitely water getting where it should not have gotten. All right. That's not my expertise. I call the building enclosure specialist who knew how to deal with that sort of thing. But it is really important that I know enough to pay the hell attention. So do please, when you're purchasing Windows, it won't be talked about here on the slides, but flashing systems are a big deal. All right. So we talked about window performance being the biggest impact on the building, right? It is super important. It's one of the largest variables you can play with in a building. And window performance itself can be broken down into pieces. And we do this in the PHINZ planning package, but even in practical terms, if you're a builder putting a window in a building, you can think about that performance of that window as a function of how it goes in the wall, which is this psi-I thing, which is, not necessarily the most useful terminology, but it's a psi install. It's like how the window fits in the wall, right? And that's the heat loss due to basically maybe the extra timber around the wall, or if the window pokes out of the building or pokes in, or I don't know, you put some metal flashing around it that goes from inside outside and causes poor performance. The function of the frame, and that's what you're buying, and the window suppliers want to talk about a lot is their frames because that's what they're selling. Whether it's UPVC or timber or aluminum with a thermal break, or overseas, you can get fiberglass and get all kinds of stuff, right? Then it's a function of the glazing edge spacer. In other words, how the glass is inserted into the frame. And that can vary a lot. If you've got an aluminum spacer, it's quite poor, all the way up to you can get spacers that are, super spacers that are like foam and desiccant and have very, very good performance. And then finally, the center of glass performance, this UG value. And generally, the things we tend to look at in New Zealand traditionally is just UG, and we start to think about UF, but not really. And that makes sense. I mean, it's some justification for that. In other words, the biggest impact on performance for the windows is generally UG, the center of glass performance. And then the next thing you look at is a frame performance. The psi-G performance is sort of set. You can't really muck around with that very much. Usually the window supplier and glass supplier have their spaces they'll use, and that's all you're going to get. But we can generally get good performance. And it is good to note that we often do get the best glass you can buy in the world imported into New Zealand, and then it's made into double or triple glazed units. It was one advantage the PHINZ designers in New Zealand had over the ones in Australia, in that we had really high performance glass available to us in New Zealand all the way from the start. So we could make double or triple glazed units, admittedly very expensively because they were handmade. Whereas early on, the Australians had no options for high performance glass. There's just no demand in the market at all. So let's talk about this. Since UG is the most important number, it's the highest one, let's talk about that for a second. So the heat flow through a window is dominated by the glass, and there's two numbers in PHPP. It's way more things to talk about, but we'll only talk about those two numbers, UG and G value, which also in New Zealand we'll hear Metro likes to use solar factor, SF, which is exactly the same as G value. It's defined the same. And then other folks like to use this solar heat gain coefficient, which is not exactly the same. It's close enough, though, generally not to worry about. Right? It's slightly lower. It's slightly lower than the G value. That's what it comes down to. So for heating, it's slightly conservative. All right, so what happens is when sun comes and it hits the window, part of the energy goes inside, and the G value, or the solar heat gain coefficient, is how much of that sunlight gets kept inside the building. Like, you simplify all the complicated mechanics of everything. It's like that number, if it's 0.6, means 60% of the sunlight that hits the glass outside of the window is kept inside the building, right? And yeah, I think that's enough we'll say about that. We've got a lot to go through. All right, so the number one pitfall for passive house designers is data for passive house planning package. You would think if you're dealing with a person that's supplying windows to you, that they would have frame data, especially if they're making millions of windows a year. That is not necessarily true. We've got two projects in the books right now, and both those projects are hanging out for frame data. In other words, they've bought the windows, they've been put in the building, they've passed their blower door test, they'd like to certify their building, and we're like, hey, we told you at pre-construction you need this frame data, and it's really important, and you didn't give it to us, so we'd like to see it now. And they're like, the window supplier told us to go fuck ourselves. Sorry, I shouldn't say that. So go pound sand. Yeah, as you can see, it was a pretty emotional. It's not fun being the certifier and having to say, hey, you really need to get that data or use this conservative number. And the conservative number, of course, causes problems with their energy model, so they don't want to use that, of course. So that is the number one pitfall. And it's a problem that stems from the designer, in my opinion, because you're the adult in the program, not the window supplier. They're kind of like they're salespeople, right? To some extent. And, they get to drink and party and have fun. And we do math and do drawings and design buildings for our clients. So it's our responsibility to make sure that the data is there before you give them money, in my opinion, right? So this is a quote, which is not from Stark. It's from I think it's from Thermodura down south. So on here, I wanted, they told me that, you want to make sure in the window quote that you've got the glass for each window, at least the laminate thickness and the type of coatings, the spacer name, the frame type, the window sizes. You want that all on the quote. If it's not on the quote, then you at least want an email from the supplier saying this is the spacers you're going to get. One of the windows they said they're holding up for frame data, they're actually not holding up for frame data. They actually have frame data. The window supplier doesn't want to tell them what spacers are in the windows. And I'm like, well, I can't take yada, yada. I actually need to know what they are because it matters. So in this window, they've said they're going to put Swiss Spacer Ultimate, which is great because that's the exact brand and model of the spacer. So they can pull the data, and I'll show you how to get that in a sec. And then the sizes, and in this case, they've done a good job. And you've even got the glass listed out for each one. And somewhere else in the quote, they tell you what this triple safety glazing, what the low E coating is, because low E is not sufficient, of course. There's a huge range of low E coatings, ranging from very inexpensive pyrolytic coatings to very expensive triple silver low E coatings so you can scratch off with your fingernail if you could get between the panes. So I personally would not recommend paying for the windows until you have data. I might give a deposit to start manufacture, but I certainly wouldn't give them the next lump of money. But once you've given a deposit, it's pretty hard to get it back. So I would want the data before you get that. And it certainly would cause some grief reduction in everyone's lives. There's only two variables in passive house planning package, this UG value and this G value or solar factor, right? What's going on is it's ignoring that. Problem with that is it's nice because it gives you two numbers, you can calculate them easy, they're easy to supply, but it doesn't give you all the information you would typically want if you want to look at thermal comfort. So in the summertime, if sunlight's directly hitting the glass, then the interior pane of glass depends on where the coating is, like how hot that glass gets. And I'll show you that in a sec, so I'll leave that explanation for later. So we'll talk about that summer temperature. So here's one European style data sheet, and it has two numbers on it that matter. The G value, which is per EN 410, and UG, which is per EN 673. And in New Zealand, of course, we're lucky because literally H1 says, tell me the UG value to EN 673, right? and it doesn't say where you get the G value or solar factor from, but it's close enough so it doesn't really matter in the end. And it's important that if you get these sheets, because the standard in Europe says to only show the UG value to 1 decimal place, and that makes sense for double glazing. For triple glazing, it doesn't make sense. So if you have a UG supplier tell you that their UG is 0.5, then in PHPP, you need to put 0.55. Because the problem is that the glass suppliers are smart and they sell different glass for different prices, and they will basically get a glass that's 0.548 and sell it as 0.5. It's on their data sheet at 0.5, right? So the reality is a lot of times when a glass is 0.5, it's not 0.482 or 0.456. It's 0.5. It's quite a bit difference. And that, of course, is 20%. That's 10% more heat loss over a fairly large area because it's all the glass area, right? So it's important to have the glass, if you're using triple glazing, have it at 2 decimal places, and just make sure you've got conservative because that can catch people out. Here's what I started talking about, solar heat on the window itself. So PHPP just has a number for the G value, right? Which just is how much sunlight that hits the glass gets kept inside the building, but it doesn't tell you how it feels sitting next to the window. And the important thing is to always put the coating on surface 2. So in this image, which is from a very old building science book from 1989, when I went to high school, when the sunlight hits that outside face, that outside face of the outside pane is 1. The inside face of the outside pane is surface 2. And that's where you want the low E coating on double or triple, it doesn't matter. The reason being is that is where most of the work is done at bouncing the sunlight back out. So that coating gets hot, right? Which makes the pane of glass on the outside get hot. The nice thing of having it on the outside pane is then it ventilates away, right? Because that outside pane is next to outside air. But instead, if you have it on the inside face, you get about 30% more heat gain in double glazing, less than triple. And the inside pane, and that's showing up in the G value. But what's not showing up is that the inside pane is considerably warmer now and can get quite hot. And when you're sitting next to it, that heat, the heat that comes off, it's just uncomfortable to sit next to. So just realize that thermal comfort is one of the things we want to talk about, and that where the coating is matters, although the G value tells you that how much energy is kept in the house overall, it doesn't tell you how much, the losses. So that's all I want to do, right? It's often useful to plot the data when you're trying to pick glass. Luckily, most suppliers will only give you a couple glasses initially, and you'll have to dig to get more. But do realize that you can get glass that ranges over quite a range of solar heat gain coefficient or solar factor on this chart, which is G value. So you can get glass that has the same U value, but has quite a bit different solar factor. And the extreme here, which is Excel and Extreme, are the 2 most common glasses that we use in New Zealand. Sorry about the hand signs to the mailman outside. He really wants to deliver a package, and I'm not leaving. So these glasses have a fairly similar U value, but they've got very different solar heat gain coefficients, and they've also got fairly similar color neutrality. Let's call it that, right? You can see they let slightly different amounts of energy through in terms of this natural light, but natural light you can see is nearly the same, right? So there's not much tint. So realize that you can get much lower solar heat gain coefficients or solar factors or G values and still have the same U value or slightly better U value and similar sunlight gains. In other words, similar daylighting in your home. And that's done through, basically they call it a double silver or triple silver low E coating on those windows. And it's a more expensive manufacturing process, but more importantly, from a pricing point of view, it's a up spec, so they charge more for it. So just realize it's not free. One reason I talk about solar G value in this is that what you've experienced over your life living in New Zealand is not necessarily true about high performance windows, right? So you may be used to the idea that you can close a curtain or blind on the inside that's white, and you'll significantly reduce the overheating in that room space, right? I've got white blinds closed in this room, which has got single glazing, bounces most of the heat out and helps keep the room quite comfortable, right? So if you have white interior roller blinds and you've got single pane clear glass, you can basically get a 70% reduction in the heat gain into that room by closing interior white blinds. That same room with triple low E glass, like you'd put it in a passive house, let's say Wellington and South, you can only get a 40% reduction, right? So in other words, they're half as effective as interior white blinds. So what you're used to thinking you can do in the space with interior blinds is not true. which is why in PastFalls we push exterior blinds so much. All right. I don't want to spend too much time on glass selection, but this is for double glazing. But you can see the cost for glass basically doubles or even triples for some of the more expensive coatings. And this is for glass assembled. This is from Metro. Metro provided these numbers. So for glass only, the glass can be as much as 3 times the price for really high performance glass. But if you look at it in a frame, and I don't know what frame this is, you can see that going from double clear, air-filled, relatively poor performance glass to really high performance double glazing, the cost increases about 30% or so. So it's still not zero, but do realize it's not 3 times the cost. All right. And do notice also that Excel here, which gives you almost the same U value as Extreme, is only about 10% more in this particular graph, whereas Extreme is like 30% more. And that's due to what's charged for the glass, right? You can see it over here in the glass prices as well. So we generally try to design our buildings around something with similar properties to Excel. And then there's a couple of vendors available in the market here locally that we can work with, even in triple glazing. And we only tend to use the lower solar heat gain coefficient, or G value, of the Extreme when we need to. Generally because the building's overglazed. And I won't get into that because that's not my pitfall to catch. Okay, next pitfall. Understanding what you have or don't have, right? And we're just about on schedule, so that's great. So one of the pitfalls is if you've got the database and you've got the windows are in the database, you've got the database in your PHPP, is understanding what the hell you actually have to install on your building. In other words, what's going to show up on site. And it's amazing how many times I've been on a project and we're going to look at the windows and we're like, we actually don't know what profiles on this window frame in this location. And that can be impactful, especially if, for example, if I was importing lift slide windows and I had all the data for a tilt turn window, which is quite common. I might not know the data for that lift slide window. I know the frame heights because I can see a CAD drawing, but I don't actually know the frame performance is. So we can estimate it and agree with the certifier, which we've done when we had projects certified for our design projects. But if there's another frame profile we hadn't thought about and we hadn't agreed with the certifier, it can cause significant grief. The databases typically only have tilt turn windows in them. And like if you see a PastFalls, they're like, oh, we've got a PastFalls certified window. Often that only means the tilt turn window has been calculated and certified. It's very unusual for them to have the whole suite of data. And I'll show you what that looks like in a little bit. Okay, so window performance. Sorry, see if I can get this to work. There we go. So window performance. Again, we're talking about the let's just jump onto the values. All right. So when we're, I guess, let me go back one. So window performance, we've talked about UG, the glass. We haven't talked about side G, so let's talk about that next. So side, because basically I'm just going to take you through this plot of window performance from the inside out, right, from the center of the glass. So top right, bottom left. So if we talk about spacers, so with spacers, luckily in most windows, spacers act reasonably similar in the same kind of frame. And that means that almost all the spacers we use, they're available in the PastFalls certification database. You can look the values up, and what's not useful is that you're supposed to add 10% to those values if you don't have actual calculations for your windows. Stark has done window calculations with their exact spacers in them, so you can use the exact side values they give you in the database to be used in PHPP, but most windows don't have that. So you might have a timber window, which is PastFalls certified with Swiss Spacer Ultimate spacers in it. But the actual windows going to come in are actually going to be a TGI spacer, right? Which is another quite good performance spacer, right? And what you need to do is you need to go look at the TGI spacer data sheet and make sure in PHP you've put the number for your frame type. So you say, oh, I've got double glazing and it's a UPVC window, so the spacer value is 0.04, right? No, it's 0.044 because you have to add 10%. It says that on the PastFalls planning certification data sheet at the bottom, but I don't know why it's not at the top in like 50-point font, because it should be. It certainly has caught me out in one of my projects early on. Luckily, it fit inside the energy, but I had to change it. So, okay. Make sure that that side G gets entered. The glass data goes into a sheet that looks like the top right, where you've got a G value and a UG, right, for the glass. And then for the glass spacer, it goes on the component sheet, and then under the windows and door frames, there's a glazing edge section. We can put the spacer, brand, and model, which I don't know why I didn't put it in here. And then there's the side G value. And you can see here, I think that's a Swiss Spacer Ultimate, which I should have brought a sample out, but I won't go grab it out of the closet at this point, which has a value of 0.023, which is quite high performance for that spacer. And that's a function of the spacer as well as the frame, as well as the fact it's triple glazing. All right. Okay, so next one. So next we'll talk about frames, finally. So again, it's really important you understand what the hell you have or don't have in the building, right? If you don't know what kind of frames you got in the building, then you can't energy model it because you don't know what it is, right? So some windows have a full suite of data, like this is a pass-fail planning, this is a PHI certification for a window, and it's actually got the UF, the frame values for all these different kinds of frames, the mullions, the door thresholds, all that kind of stuff. That's really, really, really unusual. There's probably 5 frames in the whole database that have this much data. Almost all of them, well, no, quite a few of them are just for the tilt turn window. And the numbers off this sheet that are most important to look at are the frame height and the UF value. So so basically, if you think about the energy loss around the frame, it's a function of the height of the frame and the UF value. So when the UF is almost always worse than the glass. Like for a good pass-fail window, this number on here is somewhere around 1, which is quite a good frame, right? But quite a good triple glazing will be below 0.6, might be even 0.5 something, right? So it's losing 40% more energy per unit of frame height or width, right? So it's important to understand both the frame height and width and the U value. And yeah, and there's lots of ways to make assumptions and stuff like that, and I won't get to that today because that's quite time consuming. All right. And on this database, you can find windows, skylights, and glazing edge bonds, what we call spacers. Glazing edge bonds is super productive because you can find almost all the ones we use in New Zealand there. Actually, I think you can find them all, to be quite honest. Skylights and windows are good to have comparisons to stuff. And then, of course, you can get local data. All right. This is such an annoying piece of crap to deal with that we put together a window database. So on our website, you can go to library, window data PHPP, and it brings up an article, which has got a URL you can link to get this spreadsheet, which is just a Google sheet with all the data in it. And this is the windows where whenever I made this slide, right? So you can see the Stark windows here. They've got both fixed, awning, tilt turns, sliding, hinges, all that kind of stuff. They've got pretty much almost complete, they've got a complete suite modeled, and the data is on there. And you can literally cut and paste this into PHP 9 or PHP 10, which is what you should be using now, right? Realize if you're using a funky, I don't know if you're using some funky profile, even maybe from Stark, you may have to get additional calculations done and put the data in yourself. If you're using another supplier that's not in this database, you'll have to find the data and put in yourself. And just be careful that you've got the frames that you're using modeled, right? You'll get UF reports from suppliers, and there is, as part of the they're all done to this European standard, ISO 177-2, which is actually the same standard we use in New Zealand for our windows again. I love when things line up because I'm an engineer and it's all about that lining up precision, right? So this report, which we did ages ago for Thermadura, actually looking at their lift slides, I think. Yeah, looking at the lift slide doors. Because again, they've got, Thermadura had certified their tilt turn windows, but they're not the lift slides in order to save some money. And so they asked us to go off and we did the calculations for their lift slide doors from at that point. Make sure you've got UF reports from your suppliers. If it's not in the database you can use. And because generating the data for this lift slide door, I think we charged, I don't know, it was a while back, so we probably charged more than we would now, but it'll be several $1,000s to do that data analysis because you got to analyze each frame and then put it together and check it and such. And if you've ordered windows in and all you've got is cross sections and no data, then you should expect to pay that fee to get that frame data or use a conservative value that might be 20, 30% higher than reality to make sure that you've captured those windows frames in a conservative fashion. One thing that often throws off buildings is that if they've only done a tilt turn window, they've often not calculated a mullion, right? And in PHP 10, you put mullions in separately. Or if you're using PHP 9 style, then you basically split the mullion and make it a fixed window and operable next to fixed and fixed next to operable to split this frame width across 2 windows. And to do that, you need to know what this frame performance is. And for a timber window, that's pretty easy to conservatively estimate a number. For a more complex UPVC window, it often requires a calculation because there can be quite a bit of stuff in here that leaks heat effectively. If you don't, what I was trying to teach here to folks going through our mentoring class was just that you can split windows. In other words, if you have this here, mullion here and you have a UF, you can put it in as two separate windows and just split the width of this mullion across each frame. So the mullion width here, instead of being 143 millimeters, is 71.5 here and 71.5 here. That's one way to do it. And it means that you're not overcounting frame area. Now, we have accepted in the past, and we probably still will, for buildings that are heating limited. In other words, they're fine for cooling, not worried about overheating. They're just worried about, are they hitting the heating demand target or heating load target? If you don't put the mullion in, if you just put the full frame width in other words, treat it like a fixed window next to a tilt turn window, then you overestimate this mullion width, which means because the frame's worse than the glass, means you've basically made a conservative assumption, right? It's not right, but it's close enough in general, right? Where it's not close enough is if you're worried about overheating, or if you're in a really hot climate and you're worried about cooling loads or cooling demand. In general, in New Zealand, that's not a concern, so we tend to accept this, although it's not correct. If you have the data entered as PASOS Plain Package 10 style, and you've got a Windows system that's got the data in the right format, then it just drops in and you don't have to worry about this, but just be aware of that. All right, another pitfall, FRSI, one of my favorite subjects. I won't get into it too much because I don't want to take the whole day talking about FRSI as much as I'd love to. But when we talk about FRSI, we're talking about surface temperatures, right? And FRSI is a ratio between the interior temperature of the surface to the outside ambient conditions relative to the air temperature inside the house to the outside conditions. So if you think about a home where it's 20 degrees inside and 0 degrees outside, and the FRSI is 0.5, that means that the surface of whatever you're talking about is 10 degrees centigrade, right? Because 20 minus 10 is 10, 10 over 20 is 0.5, right? Because the outside's 0 and it's 20 inside, so 20 minus 0 is 20. Anyways, so it's a ratio. And all it tells you is what the surface temperature is. It doesn't tell you what's going inside the component, or if it's molded behind the jib, or whatever the hell is going on inside the wall or inside the frame. It just tells you surface temperatures, right? And it tells you surface temperature in a very special way. In other words, when we do that surface temperature, we have to convert the air temperature to the temperature on the surface of the component. And we do that by applying a surface resistance on the inside of that window or the inside of the wall or floor that's conservative. In other words, maybe you have curtains shut, or you've got a couch against the wall, or it's in a corner where you don't get a lot of airflow. So that surface resistance is actually artificially set high to about 0.2, it's set to 0.25, right? And what that means is that the energy from inside is getting into the frame of the window slower than the energy is basically going out the outside. So it makes the temperature colder on the surface, right? So that's conservative. And that's used to predict mold growth. So I'll show you in a sec. Actually, I won't show you what that looks like in PHPP because I don't have that screenshot in the next slide. I took it out because we had too many slides. But on PHPP, so this is what an FRSI calculation looks like for a door sill. So you should do an FRSI calculation effectively twice if you want to think about doing it accurately. Once you would do just a frame, and that's what this calculation is over on the left here, where the FRSI is 0.7 right at the junction of the glass and the frame. And this is quite a good setup. And you can see on this bottom, it's black, which means that surface is adiabatic. You can also think about it, it's infinitely insulated along that surface. So when you run the calculations across this timber frame window on it's a UPVC thermal break and then aluminum door sill, that FRSI tells you what's going on the frame itself and on the glass, right? And that's what's going on over here. But you also have another FRSI, which is this same door sill now sitting on the edge of a piece of concrete. And that now has a much lower FRSI, 0.43, not 0.7. And that's the FRSI due to the fact that the concrete's basically the cold soaking into the concrete and getting under the door sill, right? And getting to the inside air where that FRSI is. So realize that there's two places where that FRSI comes in. And for typical window or door, you'll typically have two FRSI numbers to kind of keep in your head, one of which is the frame or door itself, and the other was the install. Now, if you're installing into a timber frame building, you can use an FRSI from a database, and I'll actually have some references to them. in just another slide or two. So we'll talk about those then. Right. And I do have this. This is from the Passive House Planning Package version 10 on the main verification sheet at the front. If you hit the little plus sign on the left next to air tightness right here, it becomes a minus when it expands down. You can see what the FRSI requirements are for this building. So this number here, this 0.57, is calculated for the specific building. So if you're designing a small single family home, 150 square meters, let's say, getting a number that's 0.56 or something like that is pretty common throughout most of the country. And that is a function of the outdoor air change rate in the home, the temperature set point inside the building, which we usually use 20 degrees centigrade. That's what we typically do. The humidity sources in the building, in other words, the number of occupants, and the ventilation rate with potentially if it has energy recovery, yes or not. All right. So what's going on is inside of Passive House Planning Package, when you tell it you have a 150 square meter home with 2.4 meter ceilings, it knows the volume of air inside that building. And when you put the ventilation system in for Passive House, you need to have a ventilation system, right? Either extract or most commonly mechanical ventilation with heat recovery. It knows the ventilation rate, and then it knows the occupancy, either the certification occupancy, or if you're a especially good designer, you'll change it to the actual occupancy, right? And if the building is a big building, 200 square meters with a couple in it, you can use the certified occupancy. You'll find the FRSI gets quite low, even down below 0.4, sometimes down south where it's cold in the winter, right? Because the climate is very cold. So when you bring that air inside through your ventilation system, it heats up to 20 degrees centigrade, and it has a very large drying potential, right? Which means the FRSI is requirements quite low and easily met by most windows, right? It's actually more difficult to meet the FRSI requirement in Auckland than it is in Queenstown for a normal sized building. Now, where this becomes particularly important is in social housing. We've done a few social housing projects, and the FRSI requirement can get quite high, like stupidly high, where it doesn't make any sense to increase it. So what you do at that point is you increase the ventilation rate, because that's what you should be doing anyways in a building that has a high occupancy. So when we were working with Kaingora, they had basically wanted to count 2 people per bedroom, not 1, and then they also wanted to count 1 person on the couch. So if you had a 1-bedroom apartment, you had 3 people in it. If you had a 2 or 3-bedroom apartment, you might have 7 people in a 3-bedroom house, which is actually designed, and it's not a house, it's actually an apartment, right? So it's fairly compact. It's a little bit bigger than, anyway, so it's fairly compact. So you had very high occupancy. So if you're in with a social housing occupancy and ventilation rate, please make sure you check this number. Because if you get much above 0.6, you can't hit it, much above 0.6 is hard to hit even with imported windows. It also means that if let's say you're in Auckland, you're designing a passive house and it's a small home for yourself, let's say, you might want to increase the ventilation rate, which costs more energy, but it lowers the FRSI requirements so that you can use a locally manufactured window, which might have a threshold that only hits, say, 0.52 or something, right? And that's just something to realize, is that you can balance your ventilation rate in your passive house to allow you to use certain doors and windows. The other thing, so this number, just I guess the last bit of technical geekery I'll get into, is this number is calculated basically assuming that there's not condensation on that surface. It's just, it's 80% relative humidity on that surface if it got to that temperature. And this next number over here, this 0.24, is literally when you start getting water on the surface, all right? And that number is only allowed for operable door sills. So by matter of right, because certification criterion Passive House Planning Package, if you had a door sill that was 0.24, which is actually pretty shitty thermal break, in this particular passive house, you could use that for a door sill, or if the profile through an operable sliding door was that, you could use that as well. You cannot use it for a windowsill. The only other place we've been allowed to use this 0.24 criteria on certified projects, which is by matter of exemption, in other words, it's not guaranteed for every project, but on a case-by-case basis, we've been allowed to do it, is when you have a sliding door, the interlocker, the mullion between the sliding bit and the fixed bit in the middle. Sometimes the interlocker can have quite poor thermal performance. And PHI has allowed us to certify buildings when the interlocker met this first criteria for FRSI, but didn't quite make it to 0.57. From memory, it was like 0.53 or something, so it's pretty close for that project. But just realize that that's important. So I guess to summarize, Pastel Plain Package does a lot of things in the moisture balance for you that allow you to use different profiles, but it means you need to know what you're doing when you're looking at Windows and PHP, so you design those two things at the same time. All right. Installation values. So we'll now go on to installation side values, and we're on the home stretch here. So if you use Pastel Plain Package, you'll notice that we've often will have a 0.04 for SI install, and that number is reasonable if the windows are installed reasonably well. All right, but it is not 0.04. In other words, that's not the right answer. It's usually close enough to get you started, and you should look at some reference ones. So this is from the PHINZ High Performance Construction Details book, which has a window install value for a window in the center of a wall with a single timber sill, and it gives you the side value over here that you can. It's 0.04, right? Great. However, that's not true for all window installs, and especially for heads, if you've not accounted for that lintel above the window in your timber wall fraction, which is relatively common in past lots projects, then you need to think about that side value for that window head, which can be 0.06, for example. And door sills can be quite different. There's quite a few values in there. Also in the same thing, you can, when you're talking about install side values, in other words, the additional heat loss by installing the window in the wall, the way the builder builds it and puts it in. Also at that same calculation, generally they can give you an FRSI for the install. And that FRSI needs to be met by that same criteria in that front sheet we just looked at in order to certify the building. And what's going on is they're trying to prevent surface mold completely from the building, right? So unlike half of new buildings being built in New Zealand, I think is the latest branch data or something like that, have mold in them, or half of all buildings they surveyed, which included quite a few new buildings, I guess is probably the right way to say it as an engineer. So be aware of FRSI calculations. You don't need to do a thermal bridge calculation for all your junctions. Actually, I think a good pass-off design has 0 thermal bridge calculations because they've just looked at a database, they've looked at a handbook, done good practice constructions, and they don't need to worry about FRSI because all their junctions are good quality, right? So they can spend the money they would have spent on doing thermal bridge calculations and spend it on the building instead. Yeah, and there's several people throughout the country that can do thermal bridge calculations, including us. One of the first places to look is the PHINZ handbook. And there's there's quite a few junctions in there, and they're all New Zealand centric. Do note that there's some shitty junctions, poor quality junctions in there. I'm supposed to not swear. So there's some junctions in there that are just in there for reference, like a solid aluminum sill installed or a door sill on the edge of a concrete slab. So those are there for reference for you, so you know what a like normal business as usual might look like. So not every junction in there is a high performance one, but there is a whole suite of high performance junctions for UPVC, timber, thermally broken aluminium. So you've got a whole suite and with the window in various positions in a wall, so you can see the benefit you can get. And super secret hint, just pulling the window back so the front of the window frame is even with the outside of the timber studs, gets you most of the benefit of sliding the window back in the wall. You don't have to put it in the center. All right. There's another series of databases that are available for you to use, some of which are really cool and moderately useful, unfortunately, because they're not constructions we use in New Zealand very much. But there are some timber ones as well. So there's 3 available downloads on Pasapedia. So you need to be in, if you're a PHINZ member, you're pretty much automatically a member of IPHA, which gives you access to this database. And there's 3 different things in here, one of which is a PDF download of a thermal bridge catalog. And the cool thing is they've got windows installed in walls with external insulation, which is not always useful, but there's some stuff. But they've got those windows basically parametrically modeled and then modeled curves so you can see where they get there, right? So the big change in this curve is because the windows basically pushed into the insulation layer like you'd want. Then they've got this other thing called the thermal bridge tool, which is a spreadsheet tool. It's an executable, unfortunately. And it's an executable that launches an interface that looks like Excel. Not sure why. Anyways, you can basically go in and edit the yellow cells, just like in Pastel's Plain Package, and get a thermal bridge out for sliding windows around in different kinds of walls. Unfortunately, the European constructions again. But if you're doing a retrofit of a concrete building with external insulation, this thing's a bomb, right? And then finally, there's a window installation thermal bridge catalog, which does include timber walls. So I encourage you, if you're doing Pastel's Plain Package design, to get your data and get your install stuff from these resources, right? And you need to log into IFA to get access to it. Finally, and perhaps most importantly, pitfall is comfort. And we're down to the last couple slides. So the comfort is actually a certification criteria. You need to meet it, right? And the way that's done in PASFAS plain package is by looking at FRSI and then thermal comfort calculations, right? On the left here, you can see a well-designed PASFAS window series. I stole this from IFA, by the way, from Pasapedia. On the right, you can see one that's not very good, right? So you can see the additional loss above the window to the threshold, to the way the threshold is built in this wall, poor quality glass, relatively poor frames, and poor install. One thing I want to make sure to point, because it's a pitfall, is that there's no longer an exemption for windows smaller than 1 square meter for thermal comfort if you're doing a certified PASFAS. Basically, PHP 10, it can handle windows that are in assemblies of windows, so you need to meet that criteria. So if your PHP has these red squares in it, that's not a good thing. You should not be comfortable at that point. You should be asking the certifier for help, or figuring out how to put in better windows, or if you're, anyways, there's lots of solutions, but just realize that if you get these red squares, you got an issue. To summarize, when you're sourcing data, you get UF and frame heights from the window supplier or from a database somewhere. You get UG and G value, again, from the window supplier, and they need to be calculated to these standards in the middle. You get SciG from either the PHI data sheets, or they can be calculated by the window supplier. And finally, you get window installs. You can either get them from the high performance construction details book, from bridge calculation, or from another database. Right? One last pitfall as designers and builders is that clients tend to consider your time as free, if you're on a fixed price contract, especially. And I've had clients come back to us when we're doing initial design and with 10 window quotes and want us to model all 10 in PHP. I really encourage you to push back on that and not do that, because it can take literally like 4 days to do that, even especially if the data is not formatted, even if the window suppliers, all 10 of those window suppliers had all the data. So be really clear with your clients that that's not a reasonable request, and that you've given them performance and then pick whatever ones they're likely to go with and go forward. I can understand why a client would want that, but it's really not reasonable. And that's probably the last pitfall we'll talk about today. Get a summary of what to provide for certification: glass data, window data, frame data, installs. Last bits of advice: make life easier on yourself. You can use windows with data available. There's our database or PASFAS certified windows. UPVC windows are generally the best cost window. Anything else costs more. Certified components are more expensive. They often perform well. And looks. I guess the rest of this we won't really worry about. Oh, and we didn't take a chance to talk about skylights, but do realize that glass performance in skylights, when you tip the window over, the glass performs very differently. You can lose quite a bit of, you gain quite a bit of U value or lose a lot of R value. And don't forget to order the door to the garage when you order your windows from your supplier, because that door or ideally have a detached garage, right? That's something we've seen a lot of. All right. I guess let's go to questions.
Kia ora, Jason. Thank you for that. Fantastic run through. And we've got a couple of questions already from the chat. So maybe be prepared to scoot back through your slides if they're relevant.
Yeah. I'll leave it up then.
Talk up. So Belle wanted to ask you to elaborate a bit more on the exterior absorptivity and emissivity values for frames. Did you want to turn your mic on, Belle, and just ask the actual question you had?
Yes, sorry. I think it was the numbers put in there. Yeah, I got a little bit mucked up because it says exterior absorptivity, one says 0.25 and 0.9. I don't know if that's an example for a white joinery on the left side and a black joinery on the right side.
No, so absorptivity and emissivity are different things.
Yes.
So absorptivity is basically how much energy is absorbed by the surface.
Yeah.
And emissivity is how much it emits, and they can often be very different. For galvanized steel, they're actually almost the same. They're both 0.9, but most materials are different. So basically, a white UPVC frame has an absorptivity around 0.25 when it's new, and it might go down to 0.4 if it gets dirty and oxidized.
Yeah.
But the emissivity is 0.9 or very close to 0.9 all the time, right? So the only thing that won't be a 0.9 emissivity is basically shiny metals will have a lower emissivity. And one way we deal with cavity cladding on buildings, let's say you have a nice, I don't know, charcoal black cladding on a building, and you've got an air gap behind it, and then your pass-faust wall like you'd like to design. And so that emissivity of that wall is 0.9, that surface. Because it's got the ventilated cavity, on the area sheet, you'll lower that value down by 0.9 again, so you get 0.81. And that basically is accounting for the benefit of the cladding, shielding you from the night sky radiation. But this here is for a white window, and this is the emissivity, and this is the absorptivity. So
For a white window. Okay,
Yeah.
so for a black window, we would go in absorptivity somewhere between the 0.8 and 0.9.
Yeah, and this would still be 0.9.
And that will still be 0.9. Okay, cool.
That's
Yes.
correct. No, I appreciate you clarifying that for everyone.
And
Cool.
Not
Thank you.
a silly question.
and the little red triangle up above the title of the header there will give you a little drop down if you mouse over it in Excel, which gives you more detailed information about that as well.
Yes, true. Yes. Thanks,
Yeah,
Edward.
I don't know if you can see my arrow, my cursor or not.
Yes. Yeah. Yes.
Good. All right. So yeah,
thank you.
these numbers came out of what you get when you hold it over here. So
Cool.
it's got a whole list for white, black, brown, red, yada, yada, yada. So
Nice. Thank you.
Jason, is that a default number, or is there a way of calculating it? Our black frame has the same kind of technology as resin cool color paint, and while it's black, it actually reflects infrared.
Yep. And if you've got a data sheet from the foil supplier will have a data sheet for that. I guarantee it.
Yeah,
And you should definitely let folks know, because they can put that number in.
100%. If you look at it through an infrared camera, it looks white. So I
cool
would
colors.
guess that it'll be a lower value than 0.8 or 0.9, which will help that overheating. So maybe that's a number that I'll try and pull together.
Yeah, it's good. Unfortunately, it will cause multiple grief because the black window frame might have helped me meet the heating requirement. But I'd rather it was correct, eh?
Yeah.
So thank you for that. I didn't realize that.
It'll
had
also
cool
mean
colors.
less movement in the frame if it's not heating up
Yeah,
so
yeah.
much. So presumably
That's
less
exactly
reinforcing
right.
needed.
Yep.
Good.
Great.
Thanks, Benji. That was very useful to add into there. In the Q&A or the chat, we had a couple of comments where Mark Anderson was talking about flashing details and different frames having different slots built into them to fit the flashing into, and then made some comments on that. And then Bjorn had a suggestion of a flashing company in Hamilton called Eurotech, which you provide the link there, and they've got some thermal performance document which Jason did for them, which you can download from their website, which shows the installation psi values using that recessed flashing system. So some good resources available there. Did you want to comment on that, Jason?
No, I like your text flashing system. I think they won some awards for it as well.
Okay.
The main thing is that it's just that flashing system is very suitable for this style window. Like this, I think this is an S8000 or something like that. UPVC window where it's got this European style interface where it's flat and it's got these ridges in it, right? So that Eurotech flashing works really well for those European style windows like that. But the particular window I was thinking about actually had wood fiber on the outside of the frame behind a metal flashing system, behind a metal covering to keep the rain off. And the flashing system just wasn't, so it was a commercial building. It was not a pass-faust. Just to be clear. So it's not one of the folks in our community. But they had a problem with the system because the flashing wasn't provided to them by the window supplier. So it's just a matter of, you're welcome to use Eurotech flashing in your own windows. I certainly think about that in a lot of our projects, or even other custom flashing systems. But think about it, is what I'm saying, right? The pitfall is just thinking you're going to order the windows and you're sorted, because they don't always come with the flashing systems. And sometimes the flashing systems aren't even thought through for New Zealand style installs. So that could be a catch. And it's a bit of a shame because not every architect is, they're better at extreme moisture than I am by far, but they're not necessarily experts in flashing system design around windows. Right?
Yep, that's a very good point. And
I feel obliged to point out, if I may, that we put a lot of effort into our flashing system to suit all sorts of different claddings. And we've also taken that through a bunch of water booth testing. So we're very confident in the E2 performance of it there. And when we quote a window job, it comes with the flashing system as part of the quote. So if you do come to us for a quote, which I recommend you do, you don't have to worry about the flashings. They're easy to use, the builders love them, and they're tested to be watertight. So that's my little 5 cents. Thank you, Jason.
Yeah, please make sure it
That's
gets on the
great,
quote. So when I'm talking to a client, I can show them that. Because it is, I mean, yeah, it is a problem, right? Because then if the client doesn't see apples to apples in front of them, it's really difficult for a client to take a Eurotech quote and a window quote from another supplier and then compare it against a quote that's got them integrated unless you add them together for them, which is what we try to do, but we don't always.
Good point.
Perfect. Yeah, so please make sure that's obvious in your quotes for the rest of us so we don't make a mistake.
Good point.
And good tip for people seeking quotes to check that is included or isn't included, because it can make quite a difference. Following on from that one, Matteo was asking about you repeating, like, I think what you said was that in terms of the installation psi value, you don't have to position the window in the center of the frame. Just putting it back in enough so it's in line with the outside of the frame is enough to get a good psi value, which personally, that's typically the sort of details I've done, is that the front face of the window aligns with the RAB or the outside of the framing rather than going particularly deeper than that unless it's been necessary for a reason. Is that correct, what you said?
That's correct. And the classic window to look at is a UPVC window. So like if you look at Stark's osmosis, we're talking about a Stark window. So the Stark UPVC window, which has an aluminum stiffener in the frame. I'm sorry, it has a steel extrusion in the bottom of the frame. So if you push that window out of the building, even say 20 or 30 mil, then the heat leaks into that steel and gets through the frame, basically cuts the frame performance in half, right? So the psi value might be like 0.12, right? And then you slide that window back until the front of the frame's even with the outside of the RAB, as you suggested. And all of a sudden it's 0.04. And then you slide it to the center of the wall and it's 0.038, right? So the additional depth of sliding it back into the center of the wall typically doesn't buy you very much. It is, now that 0.02 is really important if you're in Germany or up high in the ranges above Queenstown, right? Because you need every little tiny bit you can get, especially for quote free, right? But often I'll set the recess of the window into the frame by the flashing system we're using, because both the Eurotech and the Stark flashings have basically a fixed depth they can work with, and they're designed to work with standard cladding systems and recess it back far enough that the window's fully inside the thermal envelope, right? Line. But pulling the window to the center of the wall isn't always the best position. Sorry, I don't want to get too much into this, but if you're talking about an ICF wall with concrete in the middle of the wall is the worst place to put it. Either put it on the outside or the inside, like push it out so the outside of the frame of the window is even with the outside of the insulation, or the inside of the building with the inside face of the frames even with the inside of the insulation. So if you put it in the middle, it's actually in line with the concrete, which means heat can get into concrete from both sides. And unless you've got additional insulation like an insulated lintel block and jam block and sill block, which you can get, and some of the better ICF suppliers provide, you can actually make it worse by putting it in the middle, which is somewhat entertaining to geeks like me.
Also, if you've got a design which is optimized right down to the limit, then putting the window slightly back into the wall does improve your psi value a little bit, which can help, but it also increases your shading on the window slightly, which can take you the other direction, which can get like you just pull your hair out if you've got hair to try and balance that. And sometimes you're better just to fix your detail and try and make everything else work around it.
Yeah, I mean, we haven't talked too much about details because we only had an hour to talk, but you can over insulate on the outside of the windows on the jambs and heads, and then over insulate on the inside on the sills. And it's quite easy to get the psi values down to 0.02 with a bit of over insulation all around. And, if you think about the inside, you just need to make sure you can still open the window above the window seat trim, right? But by leaving the sill not over insulated on the outside, you can still use the flashing and drainage nice and clear, but you can over insulate over the jambs and the heads without really causing much of a weather tightness problem. And that works really well on UPVC or timber where they've cut back the aluminum cladding. It doesn't work with a dam on timber aluminum windows where you've got basically insulating over the aluminum doesn't buy you very much. Just be aware of that. I've gotten bit by that before.
Yeah. Okay. Some of the questions which I made notes of during the presentation is that when you're going through the different elements that make up the window performance, part of that is the frame, is that have you got any kind of guidance or suggestions around when you're testing different frame options? For instance, if you get a timber window option, quite often the UF can be a bit lower, but also you end up with a wider frame. So you're reducing the glass in your window and increasing the frame in your window. Is there any particular guidance or rules of thumb around that, or is it just like go for the thinnest frame, the best performance you can get, and kind of head in that direction?
In general, that you want the thinnest frame you can. I didn't want to talk too much about frames today because there's a lot of other things to talk about, but basically timber window technologies went through kind of 3 generations in the PastFiles community. And the first generation is kind of like a normal timber window, and they had kind of they didn't have very good spacers. So they stuffed the glass way down into the frame to kind of get the glass performance up. But the timber frame was like a normal window like you'd see in a 100-year-old house in New Zealand, right? Just with double glazing and then triple glazing. And then they wanted to make the glass even thicker to have like a 420, 424 kind of glass. So they made the frames much bigger, which meant they had to get taller because they wanted the frame aspect ratio to be stiff enough. And that's kind of the second generation timber windows, and that's what most PastFiles windows are like. As you make the glazing thicker and the performance gets higher, the frame just gets thicker and also taller. So there's more frame thickness. This width between this UF between the green line and the red line gets bigger, which cuts down your glass area. So you lose heat gain from the glass as well as you lose performance. Then they went to third generation technology where they tipped the frame over and made it stick into the window like a curtain wall. So the frame thickness got quite narrow. And unfortunately, the one window supplier in New Zealand that had that, which was SmartWin, was the franchise, went bust. So there's only a few buildings. And those buildings really had trouble staying PastFiles because that really thin frame really made the performance of the windows super sporty. So the only building I know that, well, there's a couple buildings with those windows in them. The Enerfit job that was done by Daryl Sang, who's on the webinar today, that home which he designed, and I did some of the PastFiles math for him on that. That building has a SmartWin window series in it. So if you look at the photos, you can see how narrow and thin those window frame profiles are. And that's third generation timber window technology. Unfortunately, other than trying to keep the window frames as thin as you can, and I generally try to make sure that if you're going to use double glazing, a UF around 1.4, which is kind of the start standard UPVC range, they're a little better than that, is kind of where you want to go for a frame. Like much better than that is really not needed for double glazing. It's often not cost effective. When you start going to triple glazing down south, you sometimes do end up wanting a better frame performance than that. It just depends on the building. And unfortunately, it's so sensitive to frame and frame height that you end up having to try different things. What we do in our initial designs and what I recommend to all my staff is just pretend every window is a tilt turn window and operable. In other words, you've got no fixed windows in the house, and just use the tilt turn window frame height and tilt turn frame performance, which is handy because that's the one that most everybody's got published, for your initial concepts, and then only change to real windows and such later on when you started getting quotes and you know the actual windows you're likely to install. Because then that means you only need to know 2 numbers about the frame, right? The frame width and the UF. Everything else you can get from by assuming glass and spacers. So that's the only way the only hint I can offer towards dealing with this frame height trade.
Okay, thanks. Yeah, as always, back to the actual numbers of what you're dealing with.
Yeah, that would work
sorry.
amazing, Jason. But then if we have operable windows and fixed windows, but what about the sliding doors? Because those ones differ quite a lot from the U-frames and the.
They do, but if you assume that every window in a house is operable, you've got quite a bit more frame height throughout the whole house. Because if you think about this, the one I'm showing right here, this UPVC window, it's, the frame height's from the red line to the green line, right? But if it's a fixed window, the red line would be right here.
Yes, then you have more gains and then
so if you just assume if you've modeled every opening separately like you would in Design PH, and if you assumed every one of those is operable, then it sort of works out most of the time. I mean, if you have a house that's got 5 lift slides in it, then yeah, you might have to do some extra work, sorry. But
would that work for a certification then? Would you accept that?
No, I will not accept that. No, that's why I said it's good for initial design to go ahead and pick the windows out and then there. Now, the other thing you can do is I've heard Joe Life talk before he became the chair, so it's not officially a PHINZ statement. He just uses the windows that are in the database we provide because he can just cut and paste them in. And if they're not in there, then he just won't use them. And certainly I know myself, I've been frustrated enough by window suppliers that I've been tempted to do that. I don't, but I certainly am tempted to. So certainly the first windows I recommend to clients because they're easy to use. And that encourages folks to put them in there. So.
Was that the question you wanted to ask, Belle, or do you have another question?
No, I've got another question. You know me. So I don't even know if I know how to ask this question properly, so bear with me. But I find myself in this last project that I have not yet launched with you, Jason, because I'm still waiting for all those numbers from the joinery. I don't want to put something that is not going to work. Is there a sweet spot out of your expertise where, let's say I've got this UPVC U framing, I cannot quite get there with my design. I would think that initially I have a good starting point out of, most of the windows facing the north and the north side, and it's not overly big or overly, the surface to volume ratio is around as good as we can get it for a single standing house and all the stuff. So if I cannot get quite there with the UPVC framing that I want to go with, and then the UG value of the glazing is I'm reaching the top point, then I'm like, oh damn, I have to go for a much better framing, performing type of joinery. Is there a sweet spot where you can tell, oh, I already know that this framing is not going to work for this house, I go for a much better one? Or like, how much can you compensate with the glazing compared to the framing system? Does that make sense?
Yeah, I mean, it's roughly an area thing, right? So you could calculate the UF times the width of the frame times the length, but it's because you can look at the frame area and the glass area in PHP and play with those numbers, but it's generally faster to just plug numbers in. So like a budget UPVC, a good economical UPVC window, try not to insult Benji by saying budget, might have a frame of 1.4 is easy to hit, right? So if you get a frame height and you can use 1.4, then pretty much you're there, right? The problem I have had, and I actually had a project where I had to apologize to the client because we didn't do the calculations right. In other words, we assumed that we could put whatever triple glazing we wanted in that frame, but framing thickness is also a constraint. Benji, what can you fit in your profiles?
Yeah, I've got a comment to make on this, and actually I just see a question popping in, which is exactly on the point. But our standard, and like you say, the cost effective, there's also a question on price. The standard product is, the frame is the Aluplast 4000. Our brand is Stark Ambience, but the frame is Aluplast 4000. And that can only fit a 41 millimeter triple glazed unit, which we can get 4, 5, and 6 mil glass. But if you have a big picture window like 2 meters by 2 meters, and it's in a extra high wind zone, we might need, if we use 6 mil glass, then the spaces we use are really small, like only maybe 12 mil spaces in order to get that in, and that starts to impact your UG value. So my comment, and I can bring it in later, is around the 8000 series, and I'm asking about R&D. So 100% we are looking at bringing and manufacturing the 8000 series here in New Zealand, and this is the perfect platform, if I may, for me to ask kind of a market research question, and maybe all the responses don't need to come in here, but if people think, or if it's a chicken and egg thing, and if there's enough demand for 8000 to make it worth manufacturing it, we will do so. So I would just put a call out there. If you've got projects you're struggling with and you think 8000, and so the Aluplast 8000 can handle a 56 millimeter triple glazed unit, and that just gives us that much more options, and I think Belen would probably make the difference on your job there. So if people could let me know, maybe you can call on any number. I'm pretty available, and just say, yes, I have a project that 8000 will make a difference on. If there's demand for like one house lot a month or a certain amount a year, it'll make sense to make it here in New Zealand, and we'd love to do that if there is the demand.
Yeah, I guess what my question is how expensive to go on a double or triple glazed unit? Like how much responsibility or pressure would you put on the glazing compared to the frame? Would you stick to a cost-effective frame and put all the money on the glazing, or would you go to a better frame and take responsibilities out of the glazing?
I think they move a little bit hand in hand, but maybe you can answer that better, Jason.
Yeah, I can give I wouldn't say unbiased, but relatively unbiased answer, which is, first thing I do is I stick to the most economical frame I can and make the glass as good as I could. And the mistake I made in a previous project is I went up to above a 41 mil thick triple glazing on an Aluplast 4000 frame, which meant it wouldn't work. So what happened was,
Sorry.
I was working on a project where basically the architect was adding more and more shading, trying to make the building so it would overheat less, of course, which is a good thing. and which meant the window performance had to get better. And I just pushed it up to a thicker and thicker triple glazed unit past that 41 millimeters, which meant with the frames I had planned on using in that building, I couldn't fit the triple glazing in it.
Yes.
So we then figured it out, and then I had to go to the client and say, hey, you need to switch from using an Alaplast 4000 series to a 8000 series or whatever. We had to order the windows from a different supplier in order to get the performance that they wanted to get their passive house. And that didn't drive very much cost. It meant switching from a local supplier. What it really drove was schedule, right? In that project. So the cost was, I think the cost was almost exactly the same, to be quite honest, but it was, you know, it was a 16-week wait, right? That worked on their schedule. It was okay. It was, everybody was happy with me afterwards. Nobody was grumpy with me. I was grumpy with myself for not paying attention to the glass thickness, because it's certainly something I've taught people before. So do be careful about that pitfall.
Yes, perfect. Thank you guys for.
Thanks, Jason. Thanks,
It
Bill.
was amazing. Thank you.
Related question for you, Jason, is that Robert's asking about passive house certified doors being quite hard to find, and so do we calculate door performance in the same way that we do for windows? Which I think the simple answer is yes, but there's perhaps some other complications you want to touch on in terms of door performance.
Yeah. So historically, the PHPP basically has the ability to enter one exterior door, well, up to one exterior door in the area sheet. It's just a U value. So if you have a good frame and a good door, and you can calculate the door performance using just a U calculation for the area, provided it's conservative, right? So you need to account for the timber. If it's a timber door with a foam core fill or something like that, you can calculate that. Of course, you can also buy a door from a window supplier, which has all those calculations done, right? And that's much more accurate. But if you, let's say you got, you know, you wanted to buy a UPVC window series for your building, but you wanted a really a timber door or a copper covered door or something crazy, then you can get a door made. It needs to be airtight and have 2 layers of seals. It needs to clearly meet the FSR requirements, or else you're going to have to pay potentially a couple $1,000, well, $1,000 anyway, to get all the frame calculations done to make sure the door complies. But you could potentially use a door that's not PASFA certified and doesn't have the calculations done if it clearly meets the requirements. The main issue is thickness. So basically any door made in New Zealand is like 40-something millimeters thick, whereas an overseas door, certainly PASFA door, is gonna be like 90 or even more thick. So just be aware of that. The least expensive door is gonna be a UPVC door with a aluminum threshold, which is normally broken, which Stark sells them. There's other suppliers that sell them as well, with a frosted glass or clear glass fully glazed. That gives you quite good performance. If you take that glass out and put a foam core in, which Stark can do for you as well, to give you an opaque front door, the performance is worse than if it was glass. So we commonly do that for doors to garages, for example. Benji, you probably have some comments to make on that. I'll let you do that.
Yeah, and I guess we're talking about entry doors as opposed to sliding doors. Although, yeah, you're right, it's common that obviously entry doors are you know, a hero moment of the home, and it's common to do something different. Glass, as you say, is the cheapest. I think the quite common is the Parkwood Duramax panel, which I think is the one you're referencing. It's not far off double glazed in terms of its, you know, center of panel U value, but it is slightly worse. If we glaze that in, it does end up as still perfectly airtight. A little bit of a chunkier look. Yeah, front doors are, there's a lot of options, and often somebody would do a different front door to maybe what the rest of the suite was. That's pretty common.
What about making me a Rainer's front door? Like a Rainer's window with an insert panel?
Now, the thing, in Europe, most front doors, there's so much demand for front doors that there's entire companies set up just to do front doors, and they will fabricate through a kind of a custom process using a bunch of different suppliers' extrusions, and they'll basically press foam into those extrusions and then supply that door and it'll go straight into the frame. There's not enough demand for front doors in New Zealand to support that manufacturing process. Without some slides, it's hard to explain, but it basically means that obviously for every house lot, there might be 20 windows, but there's only one front door. So, you know, net demand for front doors is pretty low. It means that we are working with kind of a couple of suppliers and a little bit of Parkwood to see if we can get a proper front door solution, the likes of what they have in Europe, but we just need kind of volume, and in our tiny nation, we're still struggling for that.
Parkwood actually lost my Rainer's corner sample for like 6 months, but they found it again for me because I loaned them that a long time ago. Because I used to live in Wanganui, which is right near Parkwood Doors, right?
That's right.
So yeah, I was really trying to twist their arm to get them to build that window, but I also got to be careful with local suppliers. I don't cause them to go bankrupt, right? Because if they're going to sell 2 front doors a year or 5 front doors a year,
it's just not worth it.
Yeah, it's hard to make it work. So,
Thanks,
I hope
guys.
that answered the question. We
discussion.
did kind of get off topic. Sorry.
Yeah, no, I think that was good. We're just about to wrap up, so I'll just ask one last question. And so when you were talking about glass spacers and getting the data off the certificate for the glass spacer, and then adding 10% to enter into PHPP, those sort of matrix of frame types and glass types and things which are on the PHI certificate don't always match very well with the type of window that you might be specifying and using on your project. And so if you, I think you were there, that one, you had it briefly, like that one. So, so if we're trying to pick, if a designer or a person doing the energy modeling is trying to pick the right value to use from a sheet like this, should they be worried about the particular specification of the window profile shown, or should they just look at the UF value and say, well, my triple glazed thinly broken aluminium has got a UF of X, Y, and Z, therefore I want the one which matches closest to that, even if the one that matches closest is shown as a timber frame on this certificate?
No, you should pick the frame type first and then go across and then look at the glass. So look at the frame type, and then you can ignore the UFs here, like they go from 0.6 to 1.17. Just pick aluminium in this case, and then find the glass that's about right. So you've got double glazing or triple glazing. Okay, well, all these are triple glazing, so I can pick the one that's closest to my frame. But if you've got double glazing in a 0.6 frame, you still want to use 0.043 plus 10%.
So ignore the U value under those, use the actual frame type.
Frame first, and then glass.
Frame first, okay.
Then glass, and finally UF is how to do it to get the most accurate result. And then, of course, if I'm in an early design, I always would look across this and pick the worst one and add 10%, because it's usually not a huge impact on buildings in New Zealand, because our UF values our U values are higher than they would be in Europe. Early in the design, it's easy to put a more conservative number in and fix it up later. Going the other way can really be painful in a design project. So.
Yeah, I mean, that's a good rule of thumb, is to just use conservative values from the start wherever possible, because one of them may catch you out if you don't.
Yeah, and also when you're looking at frame performance, please make sure you always look at the timber window that's got this little green bit here. So that's a bit of steel that represents the continuous U channel that goes in the timber window, and that's missing from some UF calculations, and that can have a reasonable impact. It's supposed to be in there, but certainly the first few calculations I did 10 years ago didn't have that because I didn't know any better. But we tend to look for it now and point it out to folks. It's amazingly easy to make mistakes on window UF calculations and FRSI calculations. Even people who do it every day, all day for decades make mistakes.
Okay.
So
that's great. Thanks. I'm actually going to ask you one last question. Just
I've got time. Go ahead.
Meant to finish, but one question. So what you've just touched on actually, and when you were talking about FRSI, in the sense that that PHPP 10 is giving it these 2 FRSI values for a project, so it's not per climate zone, it's per individual project. And from what you're showing on the windows, the FRSI on the verification page is picking up those red comfort issues on the Windows sheet, so those will show up as an error if you've got those. Does that mean, though, that there's other parts of PHPP where designers need to enter FRSI values, like for every thermal bridge calculation they put on the area sheet, or anywhere else in PHPP that we need to put in FRSI values?
So it's good practice if you've done a SciCalc and an FRSI calc to put it in the sheet, so then it shows up. It'll also flag an error for you and show you've got an error in your PHPP, which is handy. But we don't require FRSI calculations for thermal bridges that are obviously going to meet the criteria. There are some certifiers that want, like some of these Australian certifiers literally want a thermal bridge calc and FRSI calc for every junction in a building. Like they want like 20 thermal bridge calculations, but that's a waste of money in my opinion, and a waste of designers' time. It's work we could do. It'd be great. We'd make money at it, but I think we can all find other things to do with our time. So So if you've got a timber junction, you generally don't need an FRSI calc, and I wouldn't expect you to put it in.
Okay, so people don't need to stress about calculating more FRSIs. It's only if they're entering thermal bridges on the area sheet, that's where they should be considering including the FRSI.
Correct, and where it's a thermal bridge where you might be concerned about the FRSI, right?
Yep.
And you can best determine that by just looking at the HPCD or another catalog and developing a feel for it.
And
yeah.
should they be looking for window data? I can't remember what you showed from your spreadsheet that includes the FRSI value for the window installation as well. So that would be the glass spacer FRSI.
Yeah, so you ideally want to have the FRSI for the windows. It's not always available. So on our window database, we've got this tiering process that Toby put together. I think tier 1 through 4, and I think the best tier is PHPP certified, which means we've got the full report including FRSI, which Stark provides. But most suppliers don't provide the FRSI calculation because it's not required by any building code across the world that I know of. So although it's an easy, almost a one-click function to get that calculation, most window suppliers don't have it. And for most windows, an experienced person, we can look at the profile and be like, that'll be fine. But for sills, like this door sill, I wouldn't know that this would be okay without running a calc. And what makes this door sill work actually is this seal right here in this corner. If this seal wasn't there, this door FRSI would be like, on the frame would be like 0.2 or something. It'd be horrible because the FRSI actually would apply way in here inside the window because you'd have air leakage all the way in. But because they have the secondary seal, which is a really non-New Zealand thing to do, by the way, that makes this Windows FRSI quite good.
Okay, thank you. That's really good. I think we're all becoming more aware of the criticality of FRSI in our designs. We'll wrap up there. Did you want
to? Could I just throw out one really quick comment on costs, because somebody did ask, and huge variation in window costs right across the country. Different, there's so many things that change it. It would be hours. But from our point of view, our standard product is around about $1,000 a square metre, locally made. To go up to triple glazing from double, that's about another $300. So that would take you up to about $1,300 a square metre of window. And then we expect Aluplast 8000 to probably be around $1,500 a square metre. All really, really rough numbers. But if you want to, you can jot those numbers down. That's $1,000 a square metre for double, $1,300 for triple, and then maybe $1,500 for Aluplast 8000. And then, there's so much variation. We've seen pricing from $500 a square metre all the way up to $4,000 a square metre for some of the aluminium systems. So that's just a comment on that.
Okay, thank you very much, Benji. I was going to say thank you very much for sponsoring the webinar and see if there's anything else you want to add. So thanks.
Well, sorry, I jumped in. Thank you.
Yeah, and I just wanted to check, Nikki, can we have the details for the next webinar to let people know? Because we have another one this month, which is on Windows again, but more of a builder's sort of social chat and what have you.
So the 29th of this month, Benji will be joining us again together with Simon Wansborough to do the Builders Social webinar on the same subject.
And what time of the day is it on the 29th?
On the 29th at 4 p.m.
4 p.m. So end of the day on the 29th. And the details for that will be on the PHINZ website where they can register for that if they haven't already?
Yes. Yeah. Everyone that has joined today automatically gets free entrance to that. So please, but you do have to register. So please go in and register so that I can give you the link.
Yeah, and so Simon teaches the certified PHPP tradesperson course, the hands-on section. Taught that several times now, both in Auckland and in Christchurch.
Yeah, Simon's a builder who's awesome. On the board at PHINZ. So great. And so thank you everyone for attending today, and thanks for all the nice kind messages about the presentation. Everyone appreciated what you've brought to us all today, Jason, and thanks for sponsoring, Benji. Really appreciate it. We'll see you all again soon.
Thank you so very much. Good weekend all.